Good day. Today we're going to discuss Module 3 of CHE 2251, Equilibrium of Force Systems. So to begin with, we define equilibrium as a condition of a system when neither its state of motion, internal energy state, tends to change with time. A body in equilibrium experiences neither linear acceleration or angular acceleration. Unless disturbed by an outside force, it will continue in that condition indefinitely. So this definition pertains to Newton's first law of motion, which is the law of inertia. The resultant of forces and moments acting on the body or a system in equilibrium is always equal to zero. So the conditions for rigid body equilibrium in two dimensions would require that the resultants for both force and couple moment at any point should be equal to zero. That is, R, or summation of F, should be equal to zero. Since it's two-dimension, this pertains now to the summation of forces along x-axis equal to 0 and summation of forces along y-axis equal to 0. And also, the summation of moments at any point is also equal to 0. These equations now are called the equations of equilibrium. So we have a free body diagram, or an FBD, is a graphical representation of forces and moments applied to a body. This is used to calculate resulting reactions in various force systems. The principle of free body diagram is to isolate the object under study and replace all supports into its equivalent forces acting on the body. We have different types of supports and connections for two-dimensional structure, and they will have different numbers and orientations of their reactions. For the first one, we have the rollers, rockers, and frictionless surface. For this type of supports, we'll have a single reaction which is directed perpendicular to the contact of surface. So for this example, our surface is along a horizontal, therefore the reaction will always be perpendicular. But if we have a horizontal surface of contact, the reaction will be along the horizontal. Next, we have a short cable or a short link. This will have a single force also, which will be directed away from the point of connection and will be oriented the same way as the orientation of the member. Next, we have a collar on frictionless rod or a frictionless pin in a slot. The force now will be directed perpendicular to the orientation of the rod or of the slot, and it will be directed away from the surface. Then next, we have a frictionless pin or hinge. Also, for a rough surface, they will have two reactions which will be parallel and perpendicular to the surface in contact. For a fixed support, we will have two reactions and one moment. We'll have a parallel and perpendicular force to the point of contact and a single rotation or moment. So to further understand our discussion, let's have some examples. So for example number 1, we have a 300-pound box held at rest on a smooth incline by a force P making an angle of 45 degrees with the incline as shown. Determine the value of P. So to solve for this problem, we have to first draw our FBD. So our x and y axis will be rotated at 30 degrees from the horizontal. So the forces acting now on our body is the applied force P, 45 degrees from the x-axis or the incline. We have the weight directed vertically down equal to 300 pounds. And since our incline is a smooth surface, therefore, we will not have a value for your friction force. We will only have a normal force which is directed towards our contact surface. So we have two approaches for this problem. The first approach is by applying our first condition of equilibrium. That is summation of forces equal to 0. So both force P and the weight will have their x and y components. So for our equation, we can have summation of forces along x is equal to 0. To the right upwards is positive. So we take the summation along x since it will be the easiest equation or simplest equation that can solve for the value of P. If we're going to use summation of forces along y, we do not know the value of normal force, so we will have a longer equation. So therefore, for summation of forces along x equal to 0, we will now have px minus wx equal to 0, or that's p cosine of 45 minus 300 sine of 30 equals 0. So simplifying, we now get the value of P equal to 212.132 pounds. A second approach is to use a force triangle. So for the first triangle, it is like drawing your forces using the polygon method. So we have here your applied force P, we have your weight, and we have your normal force. So you can draw your forces in your first triangle in no particular order. So with this, the angle now between P and the normal F or normal force is taken as 45 degrees, and the angle between the normal force and your weight is equal to 30 degrees. So from here, we can apply your sine law, in which we will have P sine over sine 30 equal to 30 pounds over sine 45, which will also give us a value of P equal to 212.132 pounds. So any of the approach will give us the same value. So next we have example number 2. Determine the horizontal and vertical components of reaction on the member at pin A and of roller B. So for this problem, we draw again your FBD first. So for pin A, as we have said, for supports, that is a pin, it will have two reactions. So for this one, we will have a horizontal reaction AH and a vertical reaction AV. So for point B, which is a roller, it will have a single reaction that is perpendicular and directed to the contact surface. So for RB, we will have your X and Y components, at which it is 30 degrees from the vertical. So to solve for our reactions, we apply the first condition of equilibrium, which is summation of forces. So we'll have summation of forces along the horizontal equal to 0. To the right, positive, we will have A horizontal minus RB horizontal equal to 0. So from the diagram, we can expand RBH, A horizontal minus RB sine of 30 equal to 0. Or we'll have AH is equal to RB sine of 30. So we have two unknowns, therefore this equation now is equation number 1. So for the second equation, we will take this from summation of forces along the vertical equal to 0, upwards positive. So we will have A vertical plus RB vertical minus 750 equal to 0. So expanding RBV from the diagram, it's now AV plus RB cosine of 30 minus 750 equal to 0. And this one now becomes our second equation. So we have now a third unknown. So to solve for the three unknowns, we'll have the third equation taken from the second condition of equilibrium, which is the condition of moments equal to 0. So for our equation, clockwise positive. So we take our moment at point A to eliminate the two unknowns AH and AV. So for our equation, we will have 750 times 3 minus RB vertical times 6 plus RB horizontal times 2 equal to 0. So simplifying, we will have 750 times 3 minus RB cosine of 30 times 6 plus RB sine of 30 times 2 equal to 0. So from this equation, we will be able to solve for the value of RB, or the reaction at support B, which is 536.205 pounds. So with the value of RB, we can substitute this to equations 1 and 2 to arrive at AH equal to 268.103 pounds and AV equal to 285.633 pounds. Example number 3. A 12-foot bar of negligible weight rests on a horizontal position on the smooth inclines. Calculate the distance at which the 100-pound load should be placed from point B to keep the bar horizontal. So to solve for this problem, we draw first our FBD. So there will be reactions at the point of contact of our bar. So we will have a normal force at points A and point B. It is a smooth incline, so there will be no frictional force. So to solve for our required value X, we first apply our first condition of equilibrium, which is summation of forces. So for NE and NB, they will have both X and Y components. So from the diagram, we can see that NE is 30 degrees from the vertical and NB is 45 degrees from the vertical. So summation of forces along the horizontal is equal to 0. To the right, positive. So our equation will be NEH minus NBH. For expanding, NE sine of 30 is minus NB sine of 45 is equal to 0. Or simplifying, NE in terms of NB will be NB sine of 45 over sine 30. Two unknowns, so this one becomes our equation 1. We take our second equation from the summation of forces vertical equal to 0. So upwards positive. So we will have NA vertical plus NB vertical minus P minus T. And that will be equal to NA cosine of 30 plus NB cosine of 45 minus 300. So this becomes our second equation. So two unknowns, two equations. We substitute equation 1 to equation 2. Thus, it will give us a value of NB equal to 155.291 pounds. So to solve for the value of X, so we take the moment at point A since we do not know the value of NE. So our equation, so summation of moments about A is equal to 0, clockwise positive, we'll have 200 times 3 plus 100 times 12 minus x minus NB cosine of 45 times 12. So this equation will give us the value of x equal to 4.823 feet. Another way to solve this problem is, instead of solving for NE in terms of NB, we solve for NB in terms of NE. So NB now is equal to NE sine of 30 over sine of 45. This one will become our equation 1. And our second equation from summation of forces vertical is still the same. So substitute equation 1 to equation 2. This will give us a value of NE equal to 219.615 pounds. Since we do not know the value of NB, we take the moment at B. So summation of moments at B equal to 0, clockwise positive, will give us an equation of NE sine 30 times 12 minus 200 times 9 plus 100 times x. And this will also give us a 4.823 feet value. So any of the solution will give us the same answer. So thank you for listening. Activity for Module 3. Please answer, evaluate problem number 1 and 4. Submission bin will be posted in the classroom.